Hi and hello to everyone. In this video, we are going to see about the semiconductor diode, its construction and its characteristic. Welcome to the lecture. Before going into the construction of semiconductor diode, we will quickly refresh what is an N-type semiconductor, what is a P-type semiconductor. Already we made a video regarding this N-type and P-type semiconductor, but still I want to say something basics related with that. Okay, a silicon or germanium in its purest form, they are called intrinsic semiconductor. Intrinsic semiconductor is of no use in any application. So what we do is we want to add some impurities. Based on the impurities, we can classify the semiconductor into N-type or P-type. These N-type and P-type semiconductors are called extrinsic semiconductor. In N-type semiconductor, the majority carriers are the electrons. You can observe that there are more minus signs here, minus symbols here, and the minority carriers are the holes. You can see only 1, 2, 3 holes are there, and the plus with the circle are called donor ions. Note that ions are not movable things, right? Only the carriers are the majority carrier is minus and the plus. Electrons and holes will be moving. So in N-type semiconductor, majority carriers are the minus, that is the electrons. Minority carriers are the plus, that is the hole. In P-type semiconductor, you can observe that the majority are the plus symbol, that they are the majority carriers. That is the holes are the majority carriers, and the minus are the, that is your electrons are the minority carriers, and the minus with the circle are called acceptor ions. Okay, so in a diode we have both N-type and P-type semiconductor, right? So we take a intrinsic semiconductor, on one half of it we will dope with the pentavalent element such that it forms an N-type semiconductor. On the other side of the silicon we will dope with the trivalent element such that we form the P-type material. So in a single silicon we have both N-type and P-type. That's the construction of a diode. Okay, so this is the symbol of the diode. So this is the anode, this is the cathode. So anode is nothing but the P, cathode is nothing but the N, right? So this is a symbol of the diode. To identify a diode, which is the cathode, this ring symbol, the silver ring symbol here, you don't know, this is the cathode. This side is the anode. Since it's a two-terminal device, we can give you a potential across the two terminals. Based on the potential, we can classify into three regions of operation. One is we are not biasing. That is, bias is nothing but applying external voltage is called biasing. Bias. Okay. If we didn't give a voltage to the diode, that is called no bias. When the applied voltage is negative, when we say reverse bias. When the applied voltage is positive, then we say it is forward bias. We will look at all the three cases. First case we are going to take. So this is the construction of a diode. Already I explained. In one side we have P, another side we have N. In P side we have more plus symbols are there, that is the holes. In N side we have more minus symbol, that is the electrons are present in the N side, right? So we don't apply any voltage. There is no bias. So Vd is equal to 0. Look at what is going to happen here. There is a concept called diffusion. Diffusion. What is diffusion? Diffusion is nothing but from higher concentration to lower concentration. Okay, you take a sponge, put it in the water. What happens? Water from the water will enter into the sponge. Why? From higher concentration to lower concentration. That is called diffusion. Okay. So if you see here, this side we have more holes are present. So what happens here? In the N side we have less number of holes, that is less number of plus symbols. Similarly in the N side we have more electrons, minus symbol. In the P side we have less number of electrons. Okay, so what happens is the holes from the P side will move into the N side. Similarly, electrons from the N side will move into the P side. This is called recombination. The electron and hole recombine. We know electron is negatively charged, hole is positively charged. So in the recombine, the charge value is get lost. Okay, so that region is called depletion region. This is the depletion region. We can see, right? What happened? The holes from the P side get into the N side. Similarly, electrons from the N side get into the P side. So thereby at the junction, we don't have any free charge carriers. Only ions will be present. Okay, right. Now look at, in the N side we have positive ion, in the P side we have negative ions. what happens is this stops further diffusion. Okay, not all the holes will be going into the n side, not all the electrons will get into the p side. Initially there will be diffusion. Once the diffusion started, the depletion region is formed. This region is called depletion region. Why it is called depletion? Depletion means absence. Free charge carriers are absent. We don't, in this region, we don't have any free electrons or free holes. Only the ions will be present. This ions forms the barrier, or I can say barrier potential, because in n side we have positive ion, in p side we have negative ion. Thereby there will be a voltage built at the junction. This voltage is called barrier voltage or built-in barrier voltage. The voltage is called barrier voltage or built-in barrier voltage. Barrier voltage, or I can say it like built-in barrier voltage. Built-in barrier voltage. This voltage stops further diffusion. Because holes will be, holes we know is positively charged, will be attracted towards a negative, but here we have positive, so holes will not move through the junction. Similarly, the electrons cannot further move through the junction. So this depletion region acts as a barrier for further diffusion. That's what explained here, right? You can pause the video. What I have explained is given here. For a silicon diode, that barrier potential is 0.7 volt. For a germanium diode, that barrier potential is 0.3 volt. So further diffusion is not possible. So when there is no bias, there won't be any current flow. So ID is equal to 0. We look into the second case, then we say it's a reverse bias. So VD is negative. Okay, VD is negative means what happens? You can see N is connected to positive, P is connected to negative. That means VD is negative. Okay, it's reverse bias. We know electrons will be attracted towards the, electrons are negative, will be attracted towards the positive. Holes are positive or attracted towards the negative of the battery, right? So what happens is the electrons from the n side will be attracted towards the battery positive. Similarly, holes from the p side will be attracted towards the negative of the battery. Thereby what happens is depletion region width widens. More charge carriers go away from the junction. So depletion width gets increased. So when reverse bias, depletion region width gets increased. So further diffusion is not possible, right? So we can also observe one thing. During reverse bias, only the minority carrier will be flowing. What is a minority carrier? I have already said that in n side, holes are the minority. In the p side, electrons are the minority. So the holes present in the p side, n side, that is the hole, you can see a hole plus symbol, will be seeing what potential? Minus potential. So this plus only will pass through the junction and get to this part. Similarly, the electrons which is present in the p side can pass through the junction and move towards the positive of the battery. So only the minority carriers can flow through the junction during reverse bias. Majority carriers cannot flow because of the increased barrier potential. That is what given. Okay, you can pause the video, make a note of it. Right, so the reverse current, what is the reverse current? You can see, look at the direction. See, diode direction, this is the arrow is in this direction, okay, from anode to cathode. When a reverse bias, what is the meaning? Anode is connected to negative, cathode is connected to positive, that is minus and plus. When minus and plus is there, this diode is going to get reverse bias. So the current is going to flow from cathode to anode. This is the cathode to anode, that is in the reverse direction. Okay, this arrow symbol is the conventional current direction, but this is in the opposite direction. That is why it is called reverse saturation current. What is reverse saturation current? Why it is happening? Reverse saturation current is due to minority charge carriers. Okay, again I will explain. In n side we have positive, very few number of positive, that's holes. In the p side, very few number of electrons, they are the electrons, minus symbol, they are the electrons. These holes will be attracted towards the minus terminal. These electrons, minority electrons in p side will be attracted towards the plus terminal. So they will be flowing. So this current is called IS. This is your IS or reverse saturation current. Reverse saturation current flows from N to T, that is your cathode to anode. Minority, so it is very small because minority carry is very small, so reverse current is also very small. So in reverse biased, only the reverse current flows and it is negligibly small. You look at the third case, we are going to forward bias. What is forward bias? I am going to connect P to the positive, N to the negative. So what happens? The majority carriers holes, that is a positive, will be attracted towards the minus terminal. Similarly, the electrons which are majority in the N minus electrons which are majority in the N will be attracted towards the positive terminal. So they can flow. So the holes will flow through the junction. The holes will flow through the junction, enters into the negative terminal. This current is called majority current. Okay, so in forward bias, what is happening? Anode is connected to positive, cathode is connected to negative. Anode is connected to positive, cathode is connected to negative. This is what happened in forward bias. Okay, in forward bias, majority carriers flows from P to N. This current is called conventional current, flows from P to N. And remember that this potential, the potential you are externally applying, or this voltage which you are externally applying, will help to overcome the barrier. I said that this barrier will stop further diffusion. Okay, because of this external voltage, the holes can overcome this positive, but it can, because of this negative, it is overcoming this positive. Okay, thereby holes are moving through the junction, N material reaches the negative of the battery, right? So during forward bias, current flows from P to N. This current direction is called conventional current direction. This is the ideal diode characteristic. We know the primary application of the diode is nothing but a switch. Okay, if you look at this axis, this side it is a VD is positive, this side VD is negative, right? So when it is VD is 0, I can say ideally forward bias. So when VD is positive, it is going to act as a closed switch. When the switch is closed, VD is 0, current can flow. We can see when VD is 0, current is increasing, this blue line. Similarly, when VD is negative, you can see anode is connected to negative, cathode is connected to positive. It is going to act as a switch is open. When the switch is open, current cannot flow. It's an open switch, right? So current is 0. So, but this is the practical diode, right? In a practical diode, what happens? We have to overcome the barrier potential. We have to overcome the barrier potential for the conduction to happen. Okay, so we will be seeing, when I forward bias, I should give a voltage which is greater than the built-in barrier potential. Then only I can see my diode will conduct. Similarly, when reverse bias, current is not 0, but it is very small. That is called reverse saturation current. And remember, reverse saturation current is due to minority charge carriers. This forward current ID is due to majority charge carriers. And note down the unit in the current axis, that is in forward current we are doing in milliampere, in reverse current is very small, we are measuring in microampere. Now we are going to model the diode. Why to model a diode? See, this is a practical diode, right? Practical diode is different from the ideal diode. In an ideal diode, we will take the current as ideal diode characteristic, already we have seen. This is the ideal diode characteristic. In a practical diode, what happens? It conducts after only 0.3 or 0.7. So we will make a voltage, threshold voltage, or I can say barrier potential, and it is having a curve of resistance, right? So this resistance indicated by this resistance 10 ohm, and this is the ideal diode. So this is the ideal diode characteristic. Sorry, it's not ideal diode characteristic, it's a practical diode characteristic. Okay, this is the ideal diode characteristic. This is the ideal diode characteristic. This is the practical diode. Practical diode will conduct after only the barrier potential. Okay, we have to overcome the barrier potential, then only it will conduct. It is not a straight line. It is having a slope that is indicated by the resistance. Okay, so these three elements, that is a barrier potential, this resistance, and this ideal diode, three combined together form the practical diode. we can see clearly all the three regions are been mentioned in this graph, right? If you look at this point, it is Vd is equal to 0. When Vd is equal to 0, there is current is 0, right? When Vd is positive, that is this axis is fully, when Vd is positive, this side of the axis is Vd is positive. After, so I can say point 1, point 2, point 3 only, it is going to start conducting, right? It is not at 0, it is not conducting. Okay, it is after point 1. This voltage is called cut-in voltage or built-in barrier potential. Okay, that this voltage is represented by Vt. Practically, this is equivalent to, this diode is equivalently represented by a voltage of 0.7 volt. For silicon it is 0.7, germanium it is 0.3. This graph they have drawn for germanium. Okay, so if it is germanium, this should be 0.3, and it is having, it's not a straight line. If it is a straight line, resistance is 0. Okay, if this is a line is like this, what is the resistance? When V is 0, current is keep on increasing. Okay, that means resistance is 0. But if you take here, it is having a some slope is there. This slope is represented by the resistance 10 ohms, and it is going to act as a switch, that is represented by the ideal diode. So these three components together constitute the equivalent of this diode. Okay, similarly, when reverse bias, what happens? When reverse bias, due to minority carriers, very small current flows, and in what direction? Opposite direction. That is why we say I is negative, is negative. You can see minus 0.1 microampere, minus 0.2 microampere. It is minus symbol is there. It indicates that it is flowing in the opposite direction. Opposite direction means minority currents flows from N to P. And why it is constant? Because minority carriers are constant, so this current is constant, right? You compare this characteristic. Ideally minority current is 0, practically it is very small. Ideally it's keep on increasing, for even for Vd is 0, but here it will conduct after only the cut-in voltage, and it is having a slope. So this is the practical current voltage or Vi diode characteristic, and this is the diode current equation, right? We can see this id is the diode current, and this is the expression, right? Is e power Vd by nVt minus 1. What is is? Is is the reverse saturation current. As I said earlier, reverse saturation current is very small. It is in very microampere or nanoampere or picoampere range. Is very negligibly small. Why it is very small? Because it is due to minority charge carriers. What is Vd? Vd is the applied voltage, the voltage which you are going to apply, or the voltage across the diode is called Vd. N is the ideality factor. Based on the construction, its value ranges from 1 to 2, but in this course we will be taking N as 1. This Vt is called thermal voltage. What is thermal voltage? Nothing but Kt by Q. What is K is? K is Boltzmann constant. We know this value 1.3 × 10 power minus 23 joules per Kelvin. T is the temperature. Very important point is temperature we are going to use in Kelvin. This temperature is in Kelvin. We can use two units for, we are using two units for temperature. One is Kelvin scale, another is degree Celsius. Okay, but note on this point here, this T we are going to use in Kelvin. So if the question is given in Celsius, you have to just add 273 degree. So Celsius plus 273 degree gives in Kelvin scale. And you know Q is the charge magnitude, that is 1.6 into 10 power minus 19 coulomb, the magnitude. So we ignore the minus 1. We ignore the minus symbol, right? Okay, so note that this is a frequent problem, because the question will be coming at room temperature. At room temperature we will take the temperature Tc as 27 degrees Celsius. So what is T? 27 plus 273, it is 300 Kelvin. So if you substitute 300 Kelvin, Boltzmann constant K, temperature 300 Kelvin divided by Q 1.6 × 19, on solving everything we will be getting 25.8. We are rounding off to 26 millivolt. This is a constant value, you have to remember, right? Okay, mostly the question is coming at room temperature, means straight away you can put Vt as 26 millivolt. N is 1. Okay, so Is will be given, that is your reverse saturation current, which is a constant. Thereby for various values of Vd you can compute the current. Okay, so we'll take a simple problem. Let us assume a diode which has a reverse saturation current as 1 picoampere. 1 pico is nothing but 10 power minus 12, and it is operated at 27 degrees Celsius. What is the meaning? At room temperature. At room temperature, what is thermal voltage? Kt by Q. K is Boltzmann constant, T is temperature. So 27 plus 273, 300 divided by Q, magnitude of the charge. On solving, we can straight away use Vt as 26 millivolt because it is at room temperature. Okay. So the question is, find the diode current and the direction for the following three cases. First is applied voltage is 0, then applied voltage is negative, then applied voltage is 0.7 volt. Okay, so we can easily solve, right? Vd is 0, can get the Vd is 0 means e power 0 is 1, 1 minus 1 0, so Id is 0. Id is 0. We can say it is in no bias. Next case you take Vd as negative. Vd is negative, right? Minus 4. Okay, so you can put Is is 1 picoampere, Vt is 26 millivolt. What is Vd in the second case? Minus 4. On solving everything, we will get the answer as minus 10 power minus 12 ampere. That is, Id is equal to Is. Id is equal to, okay, when that is your second case, when Vd is negative, you will get Id is equal to minus Is. Okay, remember this minus sign says that Id is flowing in the opposite the negative direction, and the magnitude is 10 power minus 12. So during reverse bias, current flows from cathode to anode. We know in a diode arrow is in this from what direction? P to N, anode to cathode. But when a reverse bias, the current is going to flow from cathode to anode. We look at the third case, that is Vd is 0.7. Now substitute 0.7 in the expression, current expression, we will be getting a current of 0.49 ampere. So it's a positive value where the what is the direction of Id? It is flows from anode to cathode. And look at the magnitudes, right? When no bias, current is 0. When reverse bias, current is very small and it is constant. Okay, you can substitute given like an assignment or homework to you. You substitute various values of Vd like minus 6, minus 9, minus 10. Whatever values you put, definitely you'll be getting Id as constant. That is your constant, that is equal to minus Is or reverse saturation current. Okay, so you can look at when Vd is positive, you will getting a 0.5 ampere, is more current, right? Thanks for listening. Do subscribe the channel. Happy learning.